And we will now go over to some of our example code. So first, I want to draw your attention in the GitHub for this. Again, at github.com, ufs-ceil/catcom CMA 2025. Xiaoyan can help anyone reach that. I apologize for the impaired font here. You will find all these resources. One of them, one of the areas within this is the source area, and that has a set of scripts. We will be covering each of these, but there'll be sections for many of them that we don't have time to explore together, but which are there for your further exploration in a structured way, in a documented way. And I would invite you to, ask questions about any of these. But we're going to be going through them in the ordering, not lexicographically, but numerically, that we see, starting in 2, with 1 having done these initial projects. So if you'd like to git clone this repo, again, if anyone has trouble reaching the repo, Xiaoyan is here she can get you pointed. So just raise your hand if anyone needs help. But by cloning this repo, you should be able to get access to these scripts, or you can go to it through the GitHub web interface and download them. So I'm going to start with FinSet, 2 _ FinSet. Okay. Now, the reason we're starting off with 2 _ FinSet here with FinSet is because the category of finite sets and functions between what we call FinSet is a setting of central importance within the Catlab area. And the primary reason for that is actually not it on its own, but the fact that when we introduced these sort of templates of sorts called schemas, and we map them into a category to instantiate them, where are we mapping to as FinSet? And so it's worth getting familiar with FinSet and the notation within it. So having opened this up in a Julia notebook, I'm going to making sure that we're using the current Julia kernel. I'm using Julia 1.11.5. Probably any other recent one will do okay, as long as it's 1.11 and later, maybe 1.11 and later. Yeah. Okay. So I've opened up this in Jupyter Notebook. If anyone needs help, please raise your hand. So I'm going to execute each of these in turn, and I'm just going to comment on to interpret what's going on here, because it's really important for understanding some later material. Within this, so we're going to be operating in the category of FinSet, and this category has your objects, which are finite sets, which represent finites, which constitute finite sets. But what's really interesting, even more so, is the morphisms between them, the arrows between them. So each of these guys here is a finite set. So a finite set here. And so this one might be the finite set in 1. This one might be the finite set 2, 3. Right? This one could be the finite set 1, 2, or something like that. And these morphisms are functions. So this one might, for example, map 1 into 2. There might be another one here, would be another one which maps 1 into 3. Each of those is a function. This mapping here would have 4 possible mappings: 2 to 1, So one of the mappings would be 2 to 1 and 3 to 1. Another would be 2 to 1 and 3 to 2. Another would be 2 to 2 and 3 to 1. Another would be 3 to 2 and 3 to 2. Oh, sorry, 2 to 2 and 3 to 2. So we're dealing here with a category where we have objects being sets, morphisms being integrated finite sets, and morphisms being these functions between them. And we're going to define such a function within here. We're going to define a function between two sets. A set of size 3, 1, 2, 3. This 3, 1, 4. And then a set of size 4. And that's what's indicated by this 4. Okay. I could actually have put FinSet 4, and it would have understood that as well. The 4 at the end indicates we're mapping into a category with 4 elements. The fact we're mapping from a category of 3 is indicated by the fact we have 3 numbers in this brackets. Now, this bracket syntax is a shorthand to indicate the function. It's to indicate what each of the elements of the source set, of the origin set, which has 3 elements, map into in the target set. So the first element maps to 3. The second element maps to 1. The third element of this source set maps to 4 in that target set. So this is a mapping from a set of size 3, 1, 2, 3, to a set of size 4. It's a very specific mapping. 1 to 3, 2 to 1, 3 to 4. Okay, that's how we encode that function. Now, having encoded that function, what can you do with it? Well, you can actually do a number of things. It understands that it's a function. So, for example, I could map a particular element run from this source set, say 2, using this function, and we'll see that 2 maps into 1. That's how I define the function, right? But more than that, I could map several different things. I can map 1 to 3, for example. More than that, I could ask, what's the domain of this function? The domain is FinSet of 3. Larger? Okay, thank you, thank you. Is this better? Okay. Would anyone want it larger? Thank you, Shani. This is valuable. Anyone would you like it larger yet? Oh, sorry. It's good. It's good. Okay. Thank you. So next we could ask for the domain of this. So in other words, what's the source of this function? So if this is the function, what's the source of it? And we can ask, what's its codomain or what's its target? And we see the source is FinSet 3. That's this guy here, right? 1, 2, 3. And the target is FinSet 4, right? So it understands this as a higher level structure. It's a function. More than that, we could ask, what's the preimage of what? What things are mapped into 1 by this function? And it will tell us, well, only 2 in the source maps into 1 in the target. So it was asking, what's the preimage of 1 here? Well, there's only 1 in this particular function. There's only 1 thing that maps into it. So it's this one right here. In our function, only 1 thing mapped into it. We could ask, okay, is this what's called a monic function? Or another word for that is it monomorphic? Meaning, for the context of sets and functions, is this injective? That's what it corresponds to. And the answer is true. There's no 2 elements of the target, 1, 2, 3, 4, FinSet 4, which are mapped to by the same thing in 1, 2, 3. So it is true that it's monomorphic. I do want to highlight that while it boils down to injectivity here, this is something we can ask of any morphism within Catlab, whether it's monomorphic. I can ask, well, what's the preimage of 2? And the answer is, well, nothing maps into 2. There isn't in this particular function anything that mapped to 2. So there's nothing. We can pretty print it. Now we're going to define another function, one that goes from FinSet. Yes, Arthur. Yep. Yep.
Okay. So
Do you want this particular function? Or? Yep. Yep. There we go.
Okay. So you define that one.
Yep.
Isn't that one with error? The morphism in the category? Yes. So how do you know what category it is? Is that
so in this case, it's a very good question. We could have explicitly said we're working in FinSet. Here, in this particular case, we're using this word fin function, and that is actually something that is referring to a morphism in FinSet. So it actually knows. Actually, I have to be careful about that. It actually applies to skeleton FinSet as well.
Okay, so FinSet is just a category of these objects are finite sets.
Finite sets and functions between them.
And functions between them. Okay.
Soon we're going to see FinRel, which is a category where objects are finite sets and morphisms are relations. And so this particular case, I set this up particularly for people who hadn't seen categories before to not be too distracted by, say, I'm introducing a category. But yes, this is implicitly we're working here. And soon we will start to be very clear about what category we're working in, and we'll see actually how we get that.
FinSet 4.
Yep. It's a category with 4, or is that a set with 4 objects?
Category.
Yes, it's not.
And these are objects.
That's right. Yeah.
So,
Yes.
Actually,
well, we have to be careful because there's in Catlab, there's a distinction between FinSet, which is actually does not collapse isomorphic objects, and skeleton FinSet, which does.
So this is skeleton.
This actually is infinite. This is okay. We'll see. There's a way to explicitly say I want to operate in skeleton. In which case, all sets of size 2 would be considered isomorphic. We can be very explicit about that. And I'll show you notation where we can do this in 1 or 2 more scripts from now. Yeah.
Can I also define specializations of this where I now am talking about sets of fruit and
yes.
mapping them?
Yes, and I'm going to show you a bit further down where you can be operating with symbols within these sets, not numbers. Right now, Arthur is reasonably these are great questions because for all intents and purposes, for the fact that FinSet 4 here is shown as 1, 2, 3, 4, it's almost begging to be interpreted as skeleton FinSet, where there's only one object of size 4. But it turns out, as we'll see, we have more flexibility than that because we're FinSet, not skeleton. I'll show that in just a sec. Does that help for now? A little bit?
Okay, so just to summarize, so FinSet
Yep.
4
Yep.
is just a shorthand for the set consisting of 1, 2, 3, 4.
Correct. And just as on the board, I showed there as being a set 2, 3 or a set 1, 2, and not collapsing those into one set of size 2. That's an indication that actually we do have more flexibility here, right? And we're going to soon see we can have actually a set of which has several symbolic things in it instead of like several symbols in it rather than just numbers. Okay, next we're going to define a fin function, building on our understanding from FinSet 4. This set was 1, 2, 3, 4 to FinSet 2, which has 1, 2 in it. And yes, please.
So like
This is great.
You can make a finite set out of any Julia object.
You can make a finite set out of any any set of elements you wish to define as the elements for it.
But I mean, so is any valid Julia object? I mean, can you?
That's right.
But any. So these.
That's my
themselves are not,
assumption.
you know, I would say they're not strongly typed, not indicated type.
Correct. Correct. We can have sets. I'm going to show you sets of symbols, but I chose that somewhat arbitrarily. I believe you can have sets of for example, strings, or in that print, and for that matter, you seem quite knowledgeable about this. So if I were to say that set in FinSet by extension has internal HOMs, there's actually a set of functions you can have in FinSet. You know, that are the functions that go from the set to 1, 2 to the set 1, 2, 3. For example, that's itself the set.
I couldn't put FinSet.
Sorry.
But I couldn't put FinSet in FinSet?
That's correct.
I mean, there's got to be some restriction.
Yes, no, that's right. That's right. Okay, so we're going to define a function from 1, 2, 3, 4 to 1, 2 here. Okay. Which is basically mapping from FinSet 4 to FinSet 2. I'm going to ask if it's monic, and the answer is it's not. It's not monomorphic. It's not injective, in other words, because there are, for example, 2 elements here, namely 1 and 2, which map to 1 in the target, right? There's 2 elements, 3 and 4, that map to 2 in the target. I'm just trying to teach the syntax because it'll be really important as we define C-sets later, or actually, excuse me, yeah, C-sets, the mappings between these C-set and FinSet. Okay, between a category C and FinSet. Okay, this is not monic. We could ask for the pre-image here of 2, and we'll get back to it as well. 3 maps to 2. That's what this one says, and 4 maps to 2.
So,
yep, please.
Please.
No, this is awesome.
But
yeah,
when you're defining that function,
yes,
you're listing the values of the function.
That's correct.
So it seems like you're assuming that the elements of the sets have some order, but they're strictly ordered.
This is a good question. That's a very good question. For this particular syntax, the answer is yes. But we're going to see that we can define functions, fin functions, in many different ways. Some of them involve dictionary lookups, where I can say this symbol maps to that, this symbol maps to that.
This square bracket notation is implicitly created.
Correct. 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 And frankly, I find as someone who you could say learned category theory on the street, you know, I'm not by training a category theorist. I'm an extensive user of category theory, and I've studied it seriously. But I will say that I find my category theory colleagues sometimes using FinSet and Scale FinSet pretty interesting. And a lot of the time that people work in FinSet here, they're treating it as Scale FinSet, and they just use this syntax and they're done with it. But we're going to see that we can define more general mappings here. So again, we have the domain of G1, this function that we defined here, the domain of it, its source, where it's coming from, the set whence it comes is FinSet 4. It's coming from this, and it's going to FinSet 2. Now, the notable thing that some of you know where I'm going with this is that that first function we defined, its codomain, where it went to, is the source of this function, where it going. So if this was our F1, I'm paying attention to what's there, and this is our G1, they are end-to-end arrows. And as many people will know, in a category, any two end-to-end arrows can be composed. And that's where this is going. So we're going to take F1 and G1, and we're going to compose them. Now, composition in Catlab is itself an operation that yields a higher level result. In other words, it knows that this is a composed quantity. That is of great interest in some cases where you're operating with symbolic models. In this case, we actually want to know what is the composed function. And so by saying force, we can get a particular function that's a result of composing these two functions we defined. So in other words, when you say just compose these two, it'll say, well, their composition is their composition. If we want to know what is the result of that as a mapping, we can say force, and I'm going to do this so commonly, I'm going to define a function to do it. And we can say force compose here. And now getting to some of Arthur's questions, we can define fin functions more generally than this. That was a particular syntax rooted more in the idea of working with skeleton of FinSet, where we only have one of size 2, one of size 3, one of size 4, one set. Here we can define an arbitrary Julia function, and we can declare a fin function based on that. In this case, mapping from a set of 4 elements to a set of 2 elements, where each of them has appropriately numbered numeric sets, 1, 2, 3, 4, and 1, 2. And I can map that, for example, on a sequence here and get back a sequence of results. You may note that this is the same. Extensionally, this function that came from this thing is the same as what I defined manually earlier. That was just showing that you can arrive at the same function by hard coding it or by characterizing a Julia function that we say treat it as a fin function. Now, beyond this, and time is moving on, so I do want to get on to FinRel here quickly. We can define fin sets as sets with other Julia elements. In this case, these are symbols in Julia. The symbol x1, the symbol x2, the symbol x3. Sounds like Arthur has been through several cycles of programming language preferences or revolutions within computer science, and I have as well. If you remember back in Lisp, this would be the same as tick 1, tick 2, tick 3, with tick being the apostrophe. So if we have a set, call it X, with these 3 symbols in it, and a set, call it Y, with these 2 symbols, we can define a mapping from the elements of X to the elements of Y. This is in the form of a dictionary. And this would map symbol x1 to the symbol y1, etc. What is the domain of it? Well, it's this set up here, which we defined, X. What is the codomain of it? I'm defining another one. And what is, this is a mapping from Y to Z. And I can find that they're end-to-end arrows, and I can compose them and get a symbolic function, a function that maps from symbols to symbols, from X to Y to Z, and have one from X to Z as the result. So this is composing 2 functions involving symbols, involving sets, symbols. So here we're operating in FinSet with special ease affordances for ease of representing working what's actually skeleton set, where we only have 1 set of each size. If that's what you're doing, it's especially natural to kind of define mappings like this and have them be completely enough for your needs. Okay, so this is FinSet, a glimpse of FinSet. We will be using this syntax a lot, and I want you to know what it means. Okay, time moves on. So what I'm going to do now, and I think with an eye, I'm going to open what's called FinRel. And I think with an eye towards time, to get us to the most valuable components, I'm going to actually go light on this one. I will simply make gestures at it. So in this next one, we're also going to be operating with a category of which the objects are finite sets. But the morphisms here, these mappings in this case, between these relations between these objects, these finite sets, are no longer going to be functions. They are going to be relations. And I'm not going to go through the code in front of you, but what you would find is just as in FinSet, we categorize FinSet where we have finite sets and functions. We have an identity function. We have a notion of composition. Composition yields for any two end-to-end arrows, yields an arrow going from the source of the first arrow to the target of the second. We have associativity of that composition. So if we have function in FinSet, if we have function f followed by g followed by h, we don't have to worry about where we put parentheses. F followed by g followed by h, that is f followed by g, and then followed by h, is the same as f followed by g and then h. We don't have to worry where the parentheses are. This is what's called associativity. And any identity morphism, any identity function composed with any other function and either got any function first or the other function first, we'll give that a look. That's true for FinSet. It's also true for FinRel. But here the map, these relations are not functions, they are relations between sets. And relations compose in ways that are associative, that honor identity. In other words, you compose anything with the identity relation, you'll get that other relation back. But the mechanics of how you compose relations are rather different. In the sense that it's more like matrix multiplication. If you can go from one set to another in a relation, you might have, a particular relation R from set X to set Y, and then another relation S from set Y to set Z. You can get from an object or from an element here in X to an element in Z through potentially multiple channels. So there might be multiple ways you can go here. And so how you end up computing composition of R and S, these relations where a given element can map to more than one thing or nothing at all, it has a somewhat different feel to it than it does with composition of functions. But it too exhibits what's called unitality and associativity, and it honors identity as part of the unitality. So I'm going to leave that as a topic so we can save time. Yes, Arthur.
Just wondered, what are the approximate limits on size of these sets?
Good questions. So you can construct very large mappings here in the size of megabytes of mappings. When you start having structures that consume gigabytes, then the normal representation of them in Catlab as in-memory data structures starts to run into some performance challenges. There is a project in the algebraic Julia ecosystem. It goes by the somewhat confusing name, perhaps, of acsets.jl, which explicitly works to allow for much larger structures by being really intelligent about what's in memory and what's not, and try to manage that for very, very large scale databases, for example.
So, how would this compare to like from the data frame?
Good question. AC sets seeks to build such data frames. Julia is a highly performant language. As a language, it is designed to offer performance at the level of hand-coded C. And it's actually quite successful if you look at the benchmarks for the Julia language that underlies this. It is not an accident that that underlies Catlab. The particular performance characteristics of this via as compared with contemporary data frame libraries, I cannot authentically give you an answer to that, but since the main person behind this is one of my mentees, I could ask him for the latest. Get back. That's okay.
Okay, I was just wondering if you knew offhand.
I don't know, but
would this be
yeah.
a viable alternative to using Python and Pandas or something like that?
Yes, I'd say in terms of certain high-level needs, yes. In terms of the broader ecosystem that supports pandas or the whole Python data analysis ecosystem, I would say that there's definitely going to be things there which are not yet present in the algebraic Julia world, but there will be affordances in the algebraic Julia world involving some aspects of scientific computing, and in terms of declarative characterization of these systems, which I'm not aware of any analog in the Python world. So I don't think it's a matter of just saying Julia is trying to only catch up to Python. I think here what we're dealing with is a kind of view of a very different way of computing, with high-level mathematically transparent representations of certain types of scientific computing structures in ways that don't have their analog in the Python world. And there are some affordances offered by that here. There are some affordances offered without question also in the Python world that are not here. I would put it that way, if that's helpful. And I could talk about specifics of that. Yeah.
So when you say abstractly formulate the composition of some equations,
That's right.
and then you said force, does it actually really compute it all, or does it do tricks like ways of evaluation?
Oh, I see what you're saying. In this case, it's computing it directly. In terms of the lazy evaluation, that does, I'm trying to think of the specifics of it. That does enter in. There is no question that there are places within this ecosystem where it tries to be really intelligent about what things are computed when. And you can actually, although we don't get into it here, you can actually have annotations of sorts, or rather specific arguments that you provide for certain declarations that will say, optimize it in this way and this way, and to allow it to be really fast in reverse computations, etc. And so there are attentions to performance in some areas. There is a huge amount of work that's been expended in, for example, incremental HOM search, so homomorphism search, to do that really intelligently in very clever ways. And once again, there's the power of great generality on the one hand, and the power of and the need to make that generality not come at great performance cost. And this ecosystem is trying to get that balance right. I don't know if that's helpful at all, but we could talk about particular projects where that's going on. I think Decompose is one of them. Algebraic ABMs is another, for example. AC sets.jl is another. Okay. Hopefully that's helpful. Anyone else want to ask a question about what you've seen thus far? I know for some this may be a buzzing, blooming confusion.
I could have a question about your first relation.
Yes, yeah, please. Yep. So, yep. So I'll go down and execute it, actually. Yep.
So I think it gave you two answers, like a 0 and a 1.
So for this relation,
Probably have to scroll down.
I will do that. Okay, sorry. So I evaluated the relation at 2 points. So I said if X is 3 and Y is 2, what's the answer? And if X is 2 and Y is 3, what's the answer? Yeah.
And can you interpret the source code for me? What is that rough error?
Sorry, this one right here, or this one?
That one.
This is less than or equal to. It's just less than or equal to. So this is a map from a FinSet 6 to a FinSet 6. So it's a set of size 6 to a set of size 6 where it's testing. And it's the relation is such that there is that two elements, an X from the first set to the Y to the second set, they have a mapping between them if X is less than or equal to Y.
And the 6s there are just to tell you the domains of X.
Correct. That's so hence domain of this. It's a FinRel of 6, and but it's a set of size 6, and this is just evaluating that mapping. Is that helpful? And if you want to see it as a matrix, like if you want to render that relation as a matrix, so some of you might know there's a relationship between FinRel as a category and a category of Boolean rings, so rings without negative operations. And this is rendering it as a table, which basically says, is there a mapping for a given element in the source set to a given element in the target set? It's a matrix because a given element in the source could have a relationship with multiple of the ones on the target. So this is rendering it as a matrix, and we can define relations as matrices, etc. Are we okay with that? Okay, so with an eye towards getting the real star of the show, Xiaoyan up here in a minute. I'm just the front man. I'm going to go to a fourth script called presenting categories. And this one also is leading up to Xiaoyan's topic. It's leading up to talking about schemas. And schemas are sort of these templates which we're going to map to FinSet and secure great power into plenty instances. But in order to understand that, you have to understand how to present categories. And the notion of presenting a category is going to be quite central here. So we're going to start this script off, and we are going to create a presentation of a category, a finite presentation of a category. So there's going to be a category, and we're going to characterize it in terms of what are called generators in relation. So the generators here are descriptions of the objects. Here there's just one object called state, and the morphisms, these arrows, and somehow I've managed. So am I supposed to use this backwards, or so here we're going to have a little category where we have a single object called state, and we have a single morphism or arrow called next here. And the idea here is to sort of mimic, as it were, at a high level, a discrete dynamical system. So the idea of state has some state in it, and we have a next mapping. Now, you're going to see this come into its own in Xiaoyan's examples, this sort of thing. But I want to emphasize this next goes from state to state. There's implicitly an identity map here from any object, OB. We have an identity map, but we don't give that because it's always there, guaranteed. So this next map is not the identity, but it does go from state to state. But you'll notice that this says free schema. So this is what we call freely presented by here. And what this means is that that this is a category, we're defining the generators, but from those generators, there's actually other morphisms implied. For example, next can be composed with next. And next can be composed with next 3 times and 4 times. Each of those will result in another morphism, another arrow, which we don't show explicitly in our declaration. This is just the generators, but which is implied, except to the degree that through the laws of categories or any relations we provide, some are guaranteed to be equal. For example, next composed with identity is next by the law of any category. Next composed with next composed with next. It doesn't matter whether you do next, next, and then next, or whether you do next and then next, next. They're guaranteed to be the same through associativity. So what I'm saying is, other than those laws which guarantee certain equivalence, and those are all ensured, if you have next composed with next, for example, that will be another morphism. It's just I don't have to give it, but it's next squared. So this internal one is next, and then this next outer one is next squared, and there'll be another one next cubed. All of that is implied by this being said to be based on a free schema. Okay, I can visualize this schema. I can visualize this category I've defined, the generate in terms of its generators. I'm not yet showing any relations. We'll be coming to those, but I can ask about the generators for this. And it tells me, well, there's 2 generators, state and next. The term generator, again, is used to imply that these are the seed things out of which others will be implied. And that's the case here, freely. I can query those generators. I can find a list of their names. I can get a reference to, for example, the next one. I can ask what's its domain and what's its codomain. I'm asking about what's the domain of this morphism called next. I'm asking what's its codomain. Its codomain is that object. I can compose it and get another morphism going from state to state. I can compose an identity on state with next, and we'll get next back. So there's knowledge here about the laws of categories in the sense if you compose identities with morphisms, you get back that original other morphism. If you compose 2 things here, next and next, you will get back a new morphism, next, because that's a category freely presented. I am now going to offer a related category, but with the other key component. I've talked about generators. I'm going to give a variant of this, which has those generators, but has a relation here. By a relation, I mean, we are going to state that while in general we want it to be freely presented by this, that it has to abide by, to be a legitimate instantiation of this category, we need next composed with next to be identity. I can impose that constraint that when I specify a category, I specify the rules for composition, and this is a rule for composition. Some of the rules for composition, like identity and next is being next, that's given by categories. I don't have to say that. Same thing with the associativity, but this one I can impose. I can elect in specifying this category that I want a set of rules for composition, rules of engagement such that next composed with next is identity. Alternatively, I could have said next composed with next is next, right? And had the item. So if you
just wondering why does it have to say ID of state and not just ID? Why can't you infer that?
Well, that's a good question. Yeah, you're saying there's only one object. In general, we're going to have categories with more than one object, and that's what we're calling. I'm not familiar with any way right now that it's smart enough to do that. Yeah, to like that. It'll say, aha, There's only one category, there's only one object here, so they must mean that. That would be a nice affordance. It's, we can add it as a request, or we can add it ourselves. Okay. So if I have this and I have a reference to this next for this one, we'll call it F2. I can see what equations, I can ask what equations apply for this category. These are called equations, these relations, and it says, aha, this is the equation. It knows about this equation. Now, I do have to tell you, there are functionalities in Catlab which take advantage of this. So for example, Xiaoyan is going to show you AC set colim, and AC set colim actually knows about these relations and is going to use them for great affordances, make certain things much easier to specify. In this case, however, there are certain areas where it's not smart enough to know how to take advantage. And this is a disappointment, but it's the current state, and they're working towards a solution to this using something called egraphs. Some of you may possibly have heard of in common. Right now, we state for this category, next composed with next is identity. It knows that we state that. It understands that's part of the definition of the category. But if we actually say, hey, compose for me next with next, and we say, hey, is this equal to identity on state? It says, I can't show that, no. And that is a limitation, and it's regarded as a significant limitation in Catlab.
So in general,
Yeah.
I mean, it looks like you could describe a general group by giving the relations.
That's right.
Composition.
Correct.
Groups. That's right.
Yeah, that's right. And
Although you can decide it in many cases, but in general, it's not.
it's, yeah.
We don't have fun.
We've only found
Well,
that.
yeah,
That's
it's
true.
exhaustive computation.
Right, that's right.
I don't think that would.
That's true. Okay, so I like where you're going. I need to learn from you. So yeah, I'd like to flesh that out. That's actually a very important point. But it's one of the reasons they need some significant power, and they're using this framework called egraphs to try to be able to reason about this more generally. But you're right, it's a big problem. Okay, I do want to show just as one final example to lead up to Xiaoyan's, and then I'm going to hand it over to the start of the show, is a schema that's it's going to presage a lot of what Xiaoyan will show. So this is going to be a schema for graphs, okay? And I'm going to erase this.
Can you say what the colon 0 B is? I mean, 0 B is like.
Oh, object. You start saying these are objects.
Object, it's not a zero, okay.
I'm sorry. I'm sorry. Yeah. Yeah.
Numbers.
Yeah. These are E and V are objects. Okay.
You couldn't put a J
So I wouldn't object to the J. Okay, so E and V are objects. Maybe it'll be easy if I just look at here this, if I display it. So we have two objects, E and V. We have a morphism going from E to V, called the source. So imagine these as edges. Imagine these as vertices. A given edge is going to have a source vertex and a target vertex. And a given vertex will have a reflexive edge, a given vertex in our graph. So imagine we have a graph here, and this is a directed multigraph with the important proviso, this is why it's called a reflexive graph, that every vertex in this graph is going to have a reflexive edge. So what I'm drawing here is not a category. What I'm drawing here is a graph, which has edges and vertices. Every edge has a source vertex, a target vertex. every vertex has an edge associated with it, a privileged edge that goes from itself to itself. Its source and its target are itself. This is going to be called a reflexive directed multigraph. Now,
So where did you say that the reflexive edge?
this is what I'm about to show you. So,
Oh, I see.
so the source is going to go, the source morphism will specify for each edge its associated vertex, right? The source of this edge is this vertex. There's a target. The target of this edge is that vertex. For each vertex, there's a associated edge, but it's not just any edge, right? It's not just any old edge. That's the reflexive edge. The reflexive edge is such that if you take it and then you take the source of it. So the reflexive edge is such that its source is the vertex. Its target is the vertex as well. So in other words, if I have a vertex V, call it this one right here, and I ask for its reflexive edge, that's an edge. It's an edge with a very special property. It picks out an edge for V that its source is V and its target is V. Whatever its reflexive edge, it is such that it goes from that vertex to that. And that's what these relations state. These relations state the property that in a reflexive reflexive directed multigraph, we have edges and vertices, we have each edge, sources and targets, and each vertex has a distinct edge which goes from that vertex to it. Having specified that, it is a unique reflexive, so it's a morphism from vertex to edge. There's only one such.
Yeah, but where did you say that? I mean, why can't I have another edge?
Well, you could have another edge. That would be fine. I mean, in a directed multigraph, we could have, in general, we could have reflexive edges, but this is a guaranteed reflexive edge. And that actually offers some nice properties when it comes to homomorphism. We're guaranteed to always have one. We might have one.
No, I just
Yeah.
fixed it.
Yeah. It's not, it's a privileged one that's kind of the head on. You know, it's the main one, but there could be others there. I don't know if that's helpful. Okay, so Xiaoyan, are you any question about this? So what we've done here is we've looked at finitely presenting categories, and just because a category is finitely presented doesn't mean that it couldn't have a number of morphisms generated from it that are not finite, are infinite, and it is very intelligent. Per Arthur's comment, it is incredibly intelligent about not needing to compute those unless it needs to.
Well, even in the first example.
Yeah, that's right. Precisely. So that's an area where it's very lazy. But what we've seen is that we can actually specify these quite large structures from generators and then from relations which guarantee certain properties. Now, Xiaoyan, what we've seen thus far are some illustrative examples, but they may seem rather unsatisfying. After all, this may seem to mimic at some high level some ideas of what a discrete dynamical system is, but where's the data? How can we specify the state of that? How can we specify the rule for updates? For that, we're going to have Xiaoyan lead the discussion for going to using this as a template that maps to FinSet in ways that can give states, a set of states, make next a function from set to set that honors these relations, that honors these guarantees, these properties. Xiaoyan, do you want to take it over? Okay. Now
So while you're transitioning, so like I know like virtually zero Julia,
Okay,
you know,
yeah.
but I've heard it asserted that you can define domain-specific languages in Julia. So is that, so did somewhere you define OB and
Exactly.
is that a domain-specific?
Precisely, and you sound like, you know, someone very, very knowledgeable on the computer science side. I'll just say that when you do that, you can actually secure many benefits that you'd otherwise look to for dependent types. So that it can actually give the appearance of having dependent types, which is a rather powerful feature, as maybe where languages with dependent types. A little bio break, sure. That sounds good. That sounds good. Shall why don't I erase that?
That's okay. I can do that.
Okay.
Yeah, maybe I can do or something.
Okay.
To see.
This board is it's like a flapping sheet. It sort of
Sorry.
flops around.
Sorry.
Really, you can prep on your computer.
That's okay. My first, then, yeah. I can just. Examples.
Sure,
Do that.
sure.
I was focused on the first thing, totally different on the basic law.
Yeah.
Then.
Yeah, I agree.
We only have the
The
yeah, we then see on the
homomorphism,
higher level, yeah.
yeah, in the product and co-product.
Yeah.
And pull back and push out and so on. Yeah, okay. Maybe I'll get some bitter coffee. Are you good, Shelly?
Thank you.
Okay.
Thank you for recording these sessions. I appreciate it,
Okay.
because I did get hit with some like surprise grading, like someone came down with something. So I have to leave now, but I wish I could stay for the rest, so I appreciate it.
Yeah.
Do you know where it will be uploaded?
I think we can send, so all the audience,
Okay.
emails and show that,
Thanks.
you know,
Yes. Yeah, I would have liked to have seen like the rewriting, the algebraic rewriting, because we do combinatorics. And I mean, I don't use it too much like in practice, but it might be cool to see how we do that.
Great, yeah, I think we have time, maybe, because there's at least two people interested in the eligibility and the graphical writing, because we in this model, we use writing.
Oh, cool.
So we can save some time and quickly introduce that, sure.
So thank you.
Yes.
So we did cross it.
Okay, that's all.
Yeah.
Oh, yeah, yeah. Oh, yeah. He really, he really would like to have the recording.
Okay.
And he also mentioned he's interested in the graphical rewriting.
Oh, okay.
So maybe.
Sure.
Because that is